Radioactive decay is a process that allows scientists to determine the absolute age of an organism. As isotopes, or unstable elements, decay, they do so at a constant rate. This constant rate allows scientists to determine how long it has been since an organism or rock began its decay. In 1903, physicists Henry Becquerel and Marie Curie won the Nobel Prize for their discovery of radioactive decay, sometimes called radiometric dating. In the time-lapse scene, beta-10, an unstable isotope of tin, has decayed into alpha-10, its stable daughter isotope. While the tin in the time-lapse was taken over only 27 hours due to a decrease in temperature, most radioactive decay takes thousands, if not millions of years. Because the rate of decay is constant, it allows scientists to determine how old materials are. Dating with radioactivity measures the time it takes for certain substances to decay, like the tin seen before. It can tell us the absolute age of a material, which means the approximate number of years before the present that the rock formed. If we look at the comic strip here, we can see that the oldest is here and the youngest is here, meaning relative age. We do not have a number associated with their age. In absolute age, or radiometric dating, it gives us an exact number before the present that the human, in this case, or rock, has formed, 21 years versus 4 years. Radioactivity is a process that involves the nucleus of an atom. If you remember from the beginning of the year that each atom has a nucleus made up of both protons and neutrons. The forces that bind protons and neutrons together in the nucleus is usually strong. However, in some atoms, the forces binding the protons and neutrons together are not strong enough and the atoms are unstable. During radioactive decay, unstable atomic nuclei spontaneously break apart or decay, releasing energy. The term for the process in which atoms decay is radioactivity. So here's our atom with both neutrons, protons, and electrons outside. And in radioactive decay, we're involving just this nucleus with our protons and neutrons. As energy is released, particles leave the nucleus of the atom. There are three types of radioactive decay. Firstly, alpha emission. In alpha decay, or alpha emission, our nucleus of our atom emits 4 particles. Our atomic mass is going to decrease by 4, and our atomic number by 2, which means that 2 protons and 2 neutrons are being released. As these particles are released, energy is emitted. Our second type of decay is beta decay. This is a type of radioactive decay in which a proton is transformed into a neutron or vice versa inside the atomic nucleus. This process allows the atom to move closer to the optimal ratio of protons and neutrons. As a result of this transformation, the nucleus emits a detectable beta particle, which is an electron. Energy is released. Electron capture is the third type of radioactive decay we're going to talk about today. Electron capture is a rare type of nuclear decay in which an electron from the innermost energy level is captured by the nucleus. This electron combines with a proton to form a neutron. The atomic number decreases by 1, but the mass number stays the same. This process still will release energy. In each type of radioactive decay, the number of protons, or the atomic number, is changing, thus producing a different element. Radioactive isotopes are atoms where the neutron in an element is different than what it should be. The number of neutrons can vary, and when this happens, it becomes an isotope. Isotopes are generally unstable and will decay over time. The parent isotope, or original isotope, will decay into a stable daughter isotope. In this picture here, we have a parent isotope undergoing radioactive decay, either gaining or losing protons, releasing energy, becoming a daughter isotope. Our most common example is uranium-238. Uranium-238 goes under radioactive decay and becomes lead-206. This process takes millions of years and will change 14 times before it becomes lead-206. The half-life for this process is 4.5 billion years. So it takes 4.5 billion years for each of these steps. Scientists use half-life to calculate the absolute age of a substance. A half-life is the time it takes for one half of the nucleus in a sample to decay into a stable isotope. If we look at this graph here, the yellow and orange is our radioactive substance. On the x-axis, we have our number in years, and in our y-axis, we have the percent of radioactive elements. At time now, or today, we have 100% of the radioactive element. The half-life would be when 100% of this decays into 50%. For this particular substance, that will happen in 5 years. If we have 2 half-lives, we would have 25% of the substance left, and that would happen in 10 years. If we calculate 3 half-lives, we have 12.5% of the substance left, and 15 years, so on and so forth. Radiometric dating, also called radioactive decay dating, is a way of calculating the absolute ages of rocks and minerals that contain certain radioactive isotopes. In radiometric dating, scientists measure the ratio between radioactive parent isotope and the daughter products in a sample to be dated. The older the sample, the more daughter product it contains. If we take a look at this graph here, this yellow-orange is our radioactive isotope, and this white part is our daughter isotope. As we get more daughter isotope, our time is also increasing. So the more daughter isotope, the more stable and material becomes, the older it gets. The physical conditions of Earth have no effect on radioactive decay. Therefore, it is always constant. So on Earth, the physical erosion, weathering, materials on Earth have zero effect on our radioactivity. So our elements and minerals always decay at the same rate. A frequent type of radiometric dating is potassium-argon method. In this method, geologists measure the ratio of radioactive potassium-40 atoms to the stable argon atoms in a sample. Given the long half-life of potassium-40, 1.3 billion years, this method can be used to date rocks that are hundreds of millions of years old. So the primo example of where they use this is the Hawaiian Islands. Our lava here, after it hardens, contains a whole bunch of potassium-40. And over billions and billions and billions of years, this potassium-40 will decay into argon-40, and we can take the samples of this hardened igneous rock right here and date them to figure out how long ago this magma was flowing across the Hawaiian Islands. Lastly, today we're going to talk about dating with carbon-14. To date organic materials, carbon-14 is used as a method called radiocarbon dating. Organic material is a substance that contains carbon and comes from living things. Carbon-14 is the radioactive isotope of carbon. Carbon-14 is continuously produced in the upper atmosphere. It quickly becomes incorporated into carbon dioxide, which circulates into the atmosphere and is absorbed by living matter. As a result, all organisms, including you, contain a small amount of carbon-14. So we use radiocarbon dating because all living things contain carbon-14. Carbon-14 is incorporated into the atmosphere, and all organisms contain carbon-14. Carbon-14 is an unstable parent isotope that, when it decays, will become carbon-12. The rate at which it decays is constant. One half-life for carbon-14, or the rate that it decays, half of its nucleus decays, equals 5,730 years. Because it decays at this constant rate, we can use the ratio between carbon-14 and carbon-12 to determine how old a substance is. Because the half-life of carbon-14 is only 5,730 years, it can be used to date recent geologic events up to about 75,000 years ago. This graphic sums up the cycle of carbon-14. During life, we get carbon-14 from carbon dioxide in the atmosphere, and after death, our carbon-14 begins to decay into carbon-12. This measurement allows us to know how long ago something died. After about 75,000 years, the rate of decay diminishes to an amount that is too small for scientists to measure. If you're completing your own notes, please answer these questions in a summary. If you're using the guided notes, please answer them at the end of your note sheet. 1. What happens to atoms that are radioactive? 2. Why can't carbon-14 be used to date material older than 75,000 years? The next 3 questions should be based off the graph. A. How long is one half-life of carbon-14? B. What percentage of carbon-14 is left after 2 half-lives? And C. Estimate the number of years that have passed since the death if the percentage of the parent isotope that remains is 20%.